Hello everyone, I am Kiran Kumar from Nature of Physics. Today topic is mechanical properties of solid strain energy or elastic potential energy. I hope all are doing well for the examination. Please do like and subscribe our channel Nature of Physics and also comment about my video. And watch full video, you will get clarity about the strain energy or elastic potential energy and diagram explanation clearly given, and also two numericals I'm going to explain. Okay student, see that strain energy, in which first I am considering this is the rigid support like a wall, and this is the floor. A person is pulling the string of length is L. There is a elongation in the string is x, and dx is the small element length, so that there is a initial length is L and elongation E is equal to x, considering by applying the external force. So the person is pulling with a force that is taken as F is the applied force, student. So derivation with the help of Young modules. So Young's modules Y, which is equal to stress divided by strain, that we can write force per unit area is stress divided by strain elongation divided by original length, so that is x divided by L. Writing here, notice one thing, that is elongation is written as x. Okay, and then continuation Young modules equation Y, which is equal to FL divided by A into x, so that from this equation force F, which is equal to YAX divided by L, so this is I can write as equation number 1. And continuation step, next one is small work done due to the elongation in the spring, that is due to small displacement dx, so that small work done, that is dw, which is equal to F into dx. See student clearly. Okay, then continuation here, the value is F replacing and integration on both sides, so that integral dw, which is equal to integral F value replacing YAX divided by L into dx. Okay, and then continuation integral dw, which is equal to W, and W, which is equal to YA divided by L, is the constant is common. Okay, now integral x into dx, and there is a basic formula, that is integral x to the power of 1 into dx, which is equal to x to the power of 1 plus 1 divided by 1 plus 1, so that here y, which is equal to W is equal to y into A divided by L into x to the power of 1 plus 1 divided by 1 plus 1. Okay, and then next step here only writing W, which is equal to YA x square divided by 2L I got. And small modification in this equation, see student, for this W, which is equal to half into Young modules into x divided by small l into x into A, writing same equation, just modification student for the resultant derivation. Okay, and in this equation L is multiplied and divided, small l is the initial length, that is multiplied and divided. And next in this equation the values are replacing, that is W, which is equal to U, that is strain energy. See there, work done in stretching a body or wire against the interatomic force is stored in the body in the form of elastic potential energy. Okay, and next one, x divided by L represent strain, change in length to the original length, that is strain. And also next one, volume also we can replace that, and V represent volume, volume which is equal to area into length. The values we will discuss and replace in the above equation, so that the continuation derivation, instead of W I am writing U. U is the strain energy or elastic potential energy, which is equal to, remaining value is half into, Y is the Young module, X by L represent strain. Okay, and next modifying this equation, so X by L into AL writing, student. Okay, and this is U which is equal to half into Y into strain into X by L also represent strain, change in length to the original length, elongation by original length, and this is AL represent the volume, A represent the area of the wire. Okay students, or area of the body. And then here almost we got the relation. First one, U which is equal to half into Y into strain is strain square into volume. This is I am writing as equation number 1, student. And then continuation derivation is, that is equal to, Y is the Young modules, so Y which is equal to stress divided by strain. Yes student, replacing in the above equation, the resultant equation now, U which is equal to half into Y into, that is Y replacing, okay, into writing, that is stress divided by strain into strain square into volume, so that strain square is get cancelled. So I got next equation, half into, this is stress into, next one strain is there remaining, into volume. Okay, now I can write this is equation number 2. And then continuation derivation, that is here the value we got with respect to Young module and strain, and second equation we got with respect to stress and strain. Next I wanted to find the equation, that is strain energy equation, in the form of stress and Young modules, so that from this equation we can write there strain which is equal to stress divided by Young modules. The equation is replaced in equation number 2, so that we will get third equation for the strain energy. So third equation is U which is equal to half into, okay, stress into strain which is equal to stress divided by Young module into volume. Okay student, and then continuation U which is equal to half into stress is stress square divided by Young module into volume. Okay, this is I can write as equation number 3. So clear explanation about the strain energy or elastic potential energy. First one with respect to Young module and strain, second one with respect to stress and strain, and third one with respect to stress square divided by Young modules, nothing but stress and Young module. So energy density, strain energy U, or we can write energy density, okay, that is energy density. Energy density representing letter U. U which is equal to, we can write U which is equal to strain energy divided by unit volume. Okay, unit volume, or simply we can write volume also. So that U which is equal to, we can write strain energy, that is capital U, divided by volume is V. Sorry for the mistake. So strain energy per unit volume, per unit volume. strain energy per unit volume is called energy density. Yes student, from equation 1 and 2 and 3 we are going to discuss about the strain energy per unit volume is energy density, that is strain energy density or elastic potential energy density. Okay student, so first equation, U is equal to half into Y into stress square into volume. Okay, so that see there here U which is equal to half into Young module into strain square into volume is written V. This is from equation number 1. Okay student, and also energy per unit volume which is equal to half into Y into strain square. Okay, so that energy per unit volume is energy density, that is representing by letter small u which is equal to half into Young module into strain square. So that is equation number writing 4 student. And also next equation is about the second. So second equation, that is U which is equal to half into stress into strain into volume V. This is from equation number 2. Okay student, and this also U divided by V from RHS side to LHS side, so which is equal to half into stress into strain, so that it is, I can write as equation number 5 respectively. And then next one from the equation number 3 writing, so that another equation is there. Yes student, U by V represent energy density which is equal to half into stress into strain, so that is equation number 5 here only represented. Okay, and next third one writing here, look at this clearly, please do comment about video. And third equation, U which is equal to half into stress square divided by Young module into volume is written V. This is from equation number 3. Okay, so that energy density writing, that is U divided by V is small u, that is energy density. Again I don't want to write directly writing there, so that is small u which is equal to half into stress square divided by Young module. This is, I can write as equation number 6. See student, clear explanation about it. And then another derivation related to this topic only, so that is strain energy which is equal to half into force into elongation. That derivation I am going to explain step by step clearly. Okay, so for this I am using equation number 2. Okay, yes, from equation number 2, that is U which is equal to half into stress into strain into volume. Okay student, in this derivation U which is equal to half into stress is writing force per unit area, and next strain is X is elongation taken in the diagram. See there, elongation is X taken here also represented. Okay, so that X divided by initial length is L into volume is area into length of the wire considering. Okay, already taken. And now anything get cancelled student here, so that LL is get cancelled and also area also get cancelled. So I am getting there U which is equal to half into F into X student. So that notice one thing here, elongation is X is equal to E elongation, so that U which is equal to half into force into elongation is E. So that U, which is equal to half into force into elongation, force into elongation, this is representing equation number 7. So everything clearly step by step I gave you, student. And next we will have two numericals. Okay, so that here we got fourth and fifth and sixth equation, energy density, that is strain energy density or elastic potential energy density with respect to equation 1, 2, 3. Okay, and then continuation here, general relation, that is strain energy which is equal to half into force into elongation. The relation also we got from the equation number 2, students. And then two numerical step by step I am going to explain here. So first problem, that is the elastic potential energy stored in a steel wire, that is 80 joules given, and length of the wire 20 centimeters and elongation of the wire is 2 centimeter given, and area in millimeters asking, student, and also Young module is given, Y which is equal to 2 into 10 to the power of 11 Newton per meter square. Okay, so the best formula for this, U which is equal to half into Young module into elongation and initial length is given, that is strain square into volume. Volume is equal to area into length, that is from the equation number 1, that is U is equal to half into Y into strain square into volume, student. Using that equation, so that values replacing in this equation, so that U which is equal to half into Young module is equal to given 2 into 10 to the power of 11 into strain is elongation, that is 2 into 10 to the power of minus 2 meter. So here elongation is given in the form of centimeter, that is converted into meters, 10 to the power of minus 2 meter. Okay, student, and square is there, whole square, elongation divided by length is equal to 20 meters given. Whole square is there, strain square into area into length again 20 meters writing. See this clearly. And continuation step 2 is get cancel, so that U which is equal to 10 to the power of 11 into 2 to the 4 into 10 to the power of minus 4. So square is there, divided by 20 into 20. Okay, student. And next one, area is A and 20 meters length is there. 120 is get cancel, student. And then continuation derivation, that is U which is equal to, this is 10 to the power of plus 7. Okay, 4, that is 400 writing into 10 to the power of 5 divided by 20 into area. So into 20. Yes, student, energy we have to replace there, I forgot, denominator 5, U value replacing now. Okay, U is equal to 80 given, student. Okay, so that 80 which is equal to 4, I can write 40 into 10 to the power of 6 area divided by 20, student. 20 once, 22 times, this is equal to 40. So I got their area which is equal to 40 into 10 to the power of minus 6 meter square, that is area which is equal to 40 millimeter square, student. Okay, 1 millimeter which is equal to 1 millimeter which is equal to 10 to the power of minus 3 meter. This is the answer for the given question. Aluminium rod with Young modules Y is equal 7 into 10 to the power of 10 Newton per meter square undergoes elastic strain. the strain is given 0.04%. Energy per unit volume in SI units is asking. Energy per unit volume U, which is equal to asking U, which is equal to capital U divided by V. That is strain energy per unit volume is energy density. That is energy per unit volume. Okay student, and here continuation derivation, that is first basic formula we have to select. In this basic formula here, strain energy per unit volume asking, Young module given and also strain given. Young module strain again using first equation only. Okay student, from equation number 1, that is U, which is equal to half into Young module into strain square. Okay student, U is equal to into volume. See student, from equation 1, U by V writing because of asking U by V. So volume from RHS side to LHS side, which is equal to Y into strain square. Half is there, 1/2. Okay, and U by V, which is equal to small u energy density, which is equal to half into Young module is 7 into 10 to the power of 10 into strain value 0.04% removed, then we can write divided by 100 whole square. So that small u, which is equal to half into 7 into 10 to the power of 10 into, okay, so this is 4 into 10 to the power of -4 whole square. So u, which is equal to half into 7 into 10 to the power of 10 into 4 just 16 into 10 to the power of -8. So this is +2 we are getting. So that u, which is equal to half into, okay, 7 into, okay student, 16 into 10 to the power of 2, that is we can write like this, 2 once and 2 8 times. So that the resultant equation u, which is equal to, so 7 8s are 56 into 10 to the power of 2, that is u, which is equal to 5600 joule divided by meter cube. Joule divided by meter cube student, because of energy density, energy by volume, energy is joules, volume is meter cube. Here I can write one more step, U SI units, that is joule divided by meter cube, and U CGS units, erg divided by centimeter cube. Erg divided by centimeter cube. Okay student, this is clear information about the strain energy or elastic potential energy, and strain energy per unit volume is energy density, that is elastic potential energy. Please do like and subscribe our channel Nature of Physics. Thank you. Please comment about my video.